Hi everybody, we're starting our lecture. The last thing that we managed to achieve yesterday was this equation dE equals to TdS minus PdV. We will talk also about other generalized coordinates and generalized forces a little bit later. What I told you is that this equation, although was developed for a very specific transition, but since we're talking about equilibrium states, and if we connect equilibrium states, this equation is very general and always holds. Okay. Now, what can we do with this equation? Because I will remind you that we talk about equilibrium, we talk about equilibrium states, but we still have no idea how exactly to find this equilibrium state, right? We wrote these definitions that in equilibrium state, the state itself is going to be independent of time. It's going to be independent of exactly how this state was reached. The only thing that matters are what are the generalized coordinates and generalized forces. They define this specific state, but how do we find it? How do we calculate it? And the idea is to use some sort of variational principle. Now, variational principles is a very general technique that is broadly used in physics. And the idea in two words is, well, something has to be at a maximal or at a minimal value. So I assume that you all studied analytical mechanics. And in analytical mechanics, the first lecture or the second lecture starts like that. Well, yes, you already know what Newton's laws are, and there are some specific laws, conservation of momentum, etc., etc. But let's forget about it, right? Let's write some sort of a general form. We call it action. What exactly this action? Well, we don't really know, but there is an action, and this action has to be maximal, right? The principle of maximal action. And there you go. You assume something that has a maximal value, and from this, only this small assumption of maximality of this action, you develop everything. The Lagrangian form of mechanics, the Hamiltonian form, Hamilton-Jacobi, if you manage to reach there, etc., etc., etc. It's all based on a very small assumption. There is an action, and the action has to be maximal. Why? It's an assumption. Minimal, sorry. Yeah, minimal action. Okay. Now, where this idea comes from? It actually comes from the idea of Fermat of how light travels. Right? The light will travel from one place to another through a path that it takes a minimal amount of time. The same idea of maximality goes also in statistical physics and many other aspects of physics. Okay, so we should find something, and this something has to be minimal or maximal. Okay, so these values of minimality or maximality are very important. The same we are going to use over here. So what is exactly minimal or maximal for statistical physics or for thermodynamics? Remember the second law as we generated it. It states the following. If we have state A and we have state B, we don't really care if they are equilibrium or not, but usually they are some sort of an equilibrium. And if there is any adiabatic transition from state A to state B, means that SB larger or equals to SA. So the entropy grows when the system evolves adiabatically from one specific state to another. The entropy will grow. So this leads to the following variational principle. If you live in a system, okay, so remember my question was, last week. I have a box and I have a lot of molecules inside. Some of them are blue, some of them are green, purple, whatever. And I have a membrane inside this. And the position of this membrane can vary. Okay, let's assume this is X. This is the position of my membrane. It can vary because it's bombarded by those molecules from the left and to the right, and it fluctuates. And the question is, okay, so what is the equilibrium position of my membrane? So I know the following. If I put the system, I will control the heat such that it won't enter my system. So I put a adiabatic boundary conditions. Okay. And somehow eventually I will put my membrane to some position X. Okay. What will happen? So the system is left alone. The membrane is some general position X, and I know that eventually it will evolve to an equilibrium, right? If the system is kept unconnected to the outside world, there is no flow of heat inside or outside. I'm not doing anything, I just started it from some specific initial conditions. What will happen? Eventually it will reach equilibrium. Since we're talking about statics here, we don't really care how much time it will take the system to reach equilibrium, but eventually it will reach equilibrium. In this equilibrium, this membrane will be somewhere, and this specific position will be the equilibrium position of my membrane inside the system. Now, the system reached to the state where the membrane is located at an equilibrium position by doing what? By maximizing its entropy. So for any process, because I reach this equilibrium process adiabatically, the entropy will only grow. This means that at equilibrium, the entropy is maximal. And this is my variational principle, right? I found something that is getting a maximal value at equilibrium. So this is the path that I can use in order to determine what is my equilibrium state is. I have to compute the entropy of the system. I will find the maximal value of this entropy. Maximal value with respect to what? Not to the energy, because the energy is kept constant because everything was adiabatic and I haven't done anything to my system. But with respect to internal constraints, okay, some internal properties, and with respect to those internal constraints, the entropy is going to be maximal. Okay, so this is the principle of how we find equilibrium. Right? We just compute entropy. The problem is that it's actually really hard to compute entropy. Yes, because we don't really understand what it is, but still we can do it. So this maximal value of entropy, if we want to plot it, looks like follows. So if we have entropy, let's assume here we have our constraint. You can imagine that this is the position of this membrane somehow, but it's a general constraint X. Okay? And this is my energy. Okay. So what do I know? I know for the first thing, it doesn't matter what is the value of this X, okay? The entropy is a growing function of energy. Okay? So it looks like something like that. So we have a 3-4 dimensional manifold, okay? And for any x, s is growing as a function of e. Great. Now, what do? We constrain the system such that we want the system has to reach equilibrium, so everything is kept constant, including energy. So I somehow, oh, I'm really bad at that. So let's assume that this is my manifold, and I cut it by a plane that's parallel to, it crosses E, and it's parallel to the SX plane. Okay. What will happen? So what it happens is that it crosses this manifold at different positions. And what I'm claiming, okay, so if you try to imagine where exactly it crosses this plane, where it crosses the manifold, I will have eventually one single line. Okay? The line where one plane crosses the manifold where S is defined as a function of E and X. And this entropy is maximal states that on this crossing line, there exists one specific point, okay? There exists one specific point, let's call it x0, where the entropy is maximal. And this specific point when the entropy is maximal of crossing of the two planes, manifold of the entropy and the plane that's parallel to the SX plane, exactly this crossing point where the crossing line is maximal, this is the equilibrium state. This is how we define equilibrium. Find the entropy, condition on a specific value of the energy, modify your internal constraints, okay? At some point you will find a maximal. This is your equilibrium state. Yes?
Can you repeat what are those violet lines again?
Okay, so this is my failing attempt to present to you a three-dimensional picture. So you have a manifold. This manifold, the purple manifold, assume that this is how S depends on E and X. So it's a think about it as a two-dimensional structure, okay? Two-dimensional plane, but it's not a fixed plane. Now, I have another plane where I fixed energy. Okay. At some specific, so you have two planes, one S as a function of E and X, and another one is a plane that goes through specific value of E, okay, and it's constant independent of S and of X. So those two manifolds somehow cross each other, okay, and the crossing produces a single line. Or maybe I'll put it somewhere here. Okay. So when they cross each other, there is a single line that's constructed due to crossing of two planes. Okay. And I'm going on this line, and I will find one specific point where this line is a maximal, where S is maximal as a function of X. I find this point, I call it x0, and this is the equilibrium. Okay. Yes?
How high you draw the line from E to...
So if you have two planes, they always, unless they're parallel, okay, there has to be a one-dimensional object that it's the crossing between those two planes. That's
you draw the... How far...
I'm very bad at drawing, so it's like think about this. Let's think about this guy. So you have, but it won't work. So you have one plane that goes like this, okay, and another plane that will go like this. And there is one specific line where they cross each other. Okay, that's it. Now, the thing is, you will always have a dependence of S on X such that it's not exactly a very nice plane, it's somehow curved, okay? And due to this curvature, there is going to be a maximal point, okay? Any other questions? Yes.
When I look at the graph like this, I instinctively think that this highest point is supposed to be unstable.
Why?
But
Yes, but.
the change in entropy must be always bigger than zero, right? So can you explain to me how, if the highest point of the graph, there's only like ways to go down, and which supposedly looks unstable, how can it be the most?
So you will see maybe today or next week that there are specific properties of how S depends on E. So for now, I only told you that S is a growing function of the energy. I haven't told you anything. The stability criteria that we will discover later will tell you something about, well, how the derivatives of S as a function of E look like, and how the second derivatives of E of S as a function of S look like. Okay? But I will discuss this later. You're absolutely right. There is some other properties that have to be hidden inside due to some stabilities. What I mean by stability, the equilibrium has to be stable. If I push my system a little bit to the left or a little to the right, if I have this equilibrium position of the membrane, I push it to the left or I push it to the right, eventually the system has to return to its original point. This is what equilibrium is about. You leave the system on its own, it reaches equilibrium, right? Now, this means something about the stability, means something about how S depends on E, all right? And how exactly this manifold that I haven't managed to draw properly looks like. I will discuss it later, okay? Yes?
What about the case where there are multiple maxima to S?
You always take the highest one. Right? So the same as what you've done in analytical mechanics, right? It's always the same questions. You assume that there is a highest or a minimal point of the action, and you take this point. That's it. Assumptions. Assumptions. Are there any crazy systems that have several maxima or minima? Yes. What happens if I have two points that seems to be equilibrium? There can be something that we call a phase transition. We'll discuss it later. Okay, so we have this. Yes?
Is there a specific name for this relationship or for this graph?
It's a variational principle. No other name that I'm familiar with. Okay, any other questions, suggestions, corrections? Okay, so this is the dependence of entropy on energy. But I still want to have, first of all, this is nice, how entropy behaves, but it's less practical. Why it's less practical? Because I don't really understand what energy is. Okay? I don't really understand, what entropy is. If I had some sort of variational principle that will describe to me the behavior of the energy, it would be much more practical, right? But
in analytical mechanics, we learned that energy is described by canonical coordinates.
Mm-hmm.
But the problem here is that we have so many different states.
Yes.
Microstates.
No, you don't care. You don't care. So this is the good question. You don't care about the microstates of the system. The only thing that you care are those coordinates, generalized coordinates that are inside your equation, okay? And that's it. This is the only thing that you care of. It's thermodynamical description. It's not a microscopical description. It's a macroscopical description. I forget, and I haven't told you anything about what happens to each single molecule. I started with the axioms. I started, what are the axioms? Thermodynamical law number 1, thermodynamical law number 2. It's assumptions about a macroscopical behavior of the system. I haven't made any connection to the microscopical world.
How can you describe energy without describing microscopic?
So in the 19th century, they had any idea about atoms? When it was proven that atoms exist? In 1907. Okay, so you don't need atoms, you don't need anything, you just need, well, there is energy. How I define energy? Well, you can say, oh, that's a jiggling of a lot of molecules, etc., etc. But you don't care about what happens inside. Okay? You can perform work on the system, you can heat it up, and this is how you define the energy. That's it. Great. So I want now, any other questions? I want now to go to the variational principle. Yes? No? Okay. To the variational principle for the energy. Okay? How will I describe it? So first of all, what we know is that for entropy at equilibrium, since S is maximal, so we know that ds to dx, and x is some coordinated sign inside my system, some constraint that I'm using, with constant e, it equals to 0. Right? In order to be maximum, the first derivative has to be 0. Okay? It's not enough for the maximal claim. We also know that d squared s to dx squared with constant energy, it is smaller than 0. So this is some sort of stability, right? This I have to assume. Great. So this is the variational principle, what it tells us about the entropy. Now I want to take those equations and describe to what happens to the energy of the system. Now, beforehand, I have taken my energy and I made it constant. In order to describe what happens to the energy, I have to make constant something else. Okay, so what is the constant that I'm doing or making? I'm taking the entropy to be constant. Okay, so S as a function of E and X, it's a constant quantity. Okay. Now, the next step is to produce some equations that look like this, but for energy. This is how my variational principle will operate. I'll start with, well, if this is a constant, I know that ds equals 0. The differential of my entropy, because I only looking on the macroscopical states for which S is constant, the differential equals to 0, and I will write it as ds to dE at constant x. dE plus ds to dx at constant E. dx will be equals to 0. Okay? Right? You're fine with that? Okay. Now, next step is to describe what dE is. So, dE equals to minus ds to dx constant energy divided by ds to dE constant x dx.
Why isn't dE 0? Didn't we say we're working with the constant energy?
What? No. This was obtained for constant energy. Now I'm working with constant entropy. Okay. We look on this and we say, well, if I manage to write this equation, whatever stands in front of dx is simply dE to dx. Do you agree with me? According to the rules of calculus. So we have minus ds to dx of E divided by ds to dE of x. Great. So here I have some sort of derivative that describes to me the variation of energy with respect to the internal constraint x. Okay. So if I'll take A as dE to dx with constant entropy, and this is constant entropy because this is my assumption was, okay. This is whatever is written over here. It's minus ds to dx divided by ds to dE. This is x, this is E. And let me rewrite it as, what is ds to dE? T, or 1 over t, right? So I have minus t ds to dx with constant energy. Okay, but ds to dx with constant energy equals to 0. Okay, so at equilibrium, we know that there is some sort of, let's call it criticality. It's not a criticality, but the first derivative of the energy is 0. Okay, so we can say, well, can be maximum, can be minimum, can be, well, whatever. So in order to find if it's indeed a variation of principle, we have to go to the second derivative now. So first derivative, great. This is equals 0. Fine. Let's go to the second derivative. So this is external point, right? Let's go to the second derivative. So the second derivative is d squared e to dx squared at s constant. So this is simply dA to dx at constant s. I have to take the derivative of this guy with respect to constant s, namely the derivative of whatever is standing inside those parentheses. So I will write it down first before taking everything. I write it down as dA to dE with constant x. So this is a chain rule, basically. dE to dx with constant s plus dA to dx with constant e dx to dx. Right? Because I don't know if the dependence, what? What is dx to dx? It's a chain rule. I know that it depends directly on e and it depends directly on x. But I'm taking, but e also depends on x somehow, so I need to perform two kinds of derivatives, partial derivatives. Dx to dx is simply 1, that's it. Okay. So out of this mess, what comes out? It is dA to dE at x, dE to dE at x. What is dE to dx at s? Well, let's write it as a. So we have dA to dE, okay, at x, and dE to dx is a, plus dA to dx at constant energy, okay, multiplied by 1. So as you said, we are operating at this extremal point where dE to dx equals to 0. Right? This is our equilibrium. So it simply equals to dA to dx at constant energy. Okay. The moment that it's a constant energy, I can start and operate on this derivative. Okay. So what I'm doing, it's simply d to dx of this large structure that I have inside. Okay. It is minus ds to dx at constant e divided by ds to d e at x, and all of this for constant energy e. Okay. Now it's a simple derivative of a ratio of two functions.
Sorry?
Yes?
Why from the top line to the second, what was the...
The assumption that I'm working at the external point, therefore a equals to 0. Okay. Great. So what we have here, so let's take the derivative of this guy. So it is minus d squared s dx squared E divided by ds to d e x, right? So I'm taking derivative only of whatever in the on the top of this ratio. And the second guy is ds to dx. So we'll have minus ds to dx at e from this. And I'm taking the derivative of 1 over ds to dx. Okay, so it is minus 1 over ds to d e x squared. And here on top I have an inner derivative of this guy with respect to dx. So it is d squared s to d x squared at ds to dx squared. Right? And that's it. Okay. Now, it looks complicated, but it's actually not. Why? Because again, we all the time work in the vicinity at this external point. So what do we know? At the external point, what happens to ds to dx at constant e? It's zero, right? Because the entropy is maximal at equilibrium, and we're working at this equilibrium. So this is simply zero, so all of this gets away. Okay. Now, look on this part. This part, we have ds to de. What is ds to de? 1 over t, so it goes up, so we have minus t d squared s to d x squared at e. Now we again work at the external point. At the external point, the system at equilibrium. What happens at equilibrium? D squared s dx squared at constant energy is less than 0. So all of this guy is greater than 0. Okay. So what this mess means eventually, the entropy, this is our axiom. The outcome of the axiom, or the second law of thermodynamics, is that at equilibrium the entropy has to be maximal. Great. The outcome of this, some sort of axiom, is that the energy for constant entropy has to be minimal. Okay. So the beauty and the somehow headache of thermodynamics, you have very small number of assumptions, and then you assume that all the functions are smooth, that you can perform a lot of derivatives, and some very general laws suddenly appear. Okay? So I'm assuming something small about the entropy, I'm inventing a function, I mess or massage all those equations a little bit, and I understand that, well, if the entropy is maximal, the energy is minimal. Okay? So the second variational principle that is much more useful for any purposes is that the energy at equilibrium for constant entropy has to be minimal. The system wants, right? There is nobody that wants anything, but the system will reach such a state where the energy is at its minimum. So variational principle. For constant S, E reaches or at minimum is minimum. Now, what this means again, this means if I'll try to plot this three-dimensional structure, so I have E, I have S, and I have X. I really don't know how to plot it. So let's assume that this is, no, not good enough. So let's assume that this is my two-dimensional manifold. So S is somehow growing with E. Okay. Now, beforehand, I put a plane. Yes.
E grows into the origin.
It's easier for me to plot it like that. Otherwise, I had to reverse the growth of S. That's it. So, beforehand, I had a constant E, so I have a plane that was vertical. Right? Now, if I'm constraining S to be constant, there is a plane that looks like this. Okay. And it crosses somehow, this two-dimensional manifold. This variational principle for constant S is maximal. We look on the crossing points where exactly this manifold crosses this plane crosses our manifold, and we'll find that the crossing point will look like this. Okay. And this x0 is where the crossing line is at minimal. Okay. Which actually E is minimal with respect to x for constant entropy. Right? Two variational principles. Yes?
I'm having trouble understanding your assumption that the entropy is constant.
What do you mean?
That's what you wrote.
Do you know what
start.
entropy is? I don't know what entropy is. Nobody really knows what entropy is yet, okay? Because it's actually, you need a microscopical definition to understand what it is. It's the amount of disorder in the system. So if I'm telling you there is a function, and the function grows, so I can also assume that this function is constant. How I make this function constant, I have no idea whatsoever so far. But I know if I make it constant, and I know that it's somehow related to heat, so I basically do not allow heat exchange with the environment, and I make the heat always constant, okay, inside the system, I can make the entropy constant. Okay? This is the idea. So if you have in mind, it's not exact, but if you have in mind that TdS is dq for a quasi-static process, then you know how to make ds equals to 0. That's the idea.
I just don't understand how, if you assume that it's a constant function, what does it mean when you start looking at the derivatives and I don't understand what it means if it's
It means a mathematical operation that I can perform when I'm taking one of the variables to be constant. That is what it means. So if your question, how exactly I make entropy constant in my lab, I have to go and make the heat almost constant. That's what I have to do.
But it's still a mathematical function that you can...
There is something that's called entropy. Okay? There is something like that. It has a microscopical meaning. You can say it's the amount of heat, but it's the something that it's called how the system is disordered. Or you can say how much the energy is spread inside the system. You can make it constant. Mathematically you can. Okay? Any other questions? Yes?
I'm confused. How did you reach that principle?
I start from the maximum principle and I reach this principle. This is what I've done in the last 20 minutes.
Yes.
So, this equation. This is the second derivative. So what happens if the first derivative is 0 and the second derivative at a given point is less than 0?
It's maximum, but it's not the energy.
What? It's not maximal, it's minimal, first of all. If it's greater than 0. It is the energy. It is the energy. What all of this was? It was equals to d square e to dx square constant s. This is what I started from. Okay? I had a bunch of equations that started over here. I did all of that and I managed to obtain that the second derivative is greater than 0. That's all. Any other questions? So let's try and see how we use those variational principle in a very trivial way to understand what happens to the system. So, two simple examples. First of all, let's assume that I have a system or two systems. Okay? So the energy of this system is E1, the temperature of the system is T1, the entropy of the system is S1. The same goes here. E1 or E2, T2, and S2. Now, those energies, temperatures, entropies are obtained after I connected those two systems. Heat was exchanged, whatever was exchanged between those two systems, and eventually those two systems are in equilibrium. So in equilibrium. Okay. So what happens in equilibrium? Okay. So specifically, I want to see how the temperatures T1 is of two systems that are in equilibrium, how they connected to each other. So is T2 larger than T1? Is T1 larger than T2? So there's two ways to start thermodynamical descriptions. There is a way to describe what happens to temperature, hot bodies, cool bodies, etc., etc., etc. And what I'm trying to describe to you in this class is we start with the description of entropy. It's very abstract, very mathematical, and everything that you have learned about temperatures, flow of energy will come out naturally from the variational principles that we now derive. Okay. So I want to obtain the connection between T1 and T2. What do? I would say if they are in some sort of equilibrium, I know that if I push the system a little bit out of this equilibrium, the entropy will go down. Delta S is smaller than 0 for any change that I will perform on the system. Okay? Why? Because the first variational principle tells me that the entropy has to be at maximum. Okay? Now, I did something, but remember when the entropy is at maximal, I haven't modified the total energy of the system. So I know that delta E1 plus delta E2 equals 0. Right? Because the energy was constant. I did something to the system. The entropy went down a little bit. You can call it a fluctuation. The energy was kept constant. Nothing happened over there. Okay? And those are my two assumptions. So when I'm saying that the entropy went down, the total entropy went down. It can be that the entropy of this guy went a little bit up, the entropy of that guy went a little bit down. The variational principle tells me something that happens to the whole system and not to some small part of it. Okay? So when I'm writing what is delta S, is S1 plus S2. So this delta S is delta of S1 plus S2, and it's simply delta S1 plus delta S2. What is the next step? So what is delta S1? It's the modification of the entropy of this system with respect to the energy, right? You can say that this is ds1 to de1 delta E1. And this guy is ds2 to de2 delta E2. Now, why I'm writing this in this form? Because whatever stands over here and over there, it's just 1 over the temperature. We define the temperature as the derivative of the energy with respect to the entropy. So we have 1 over T1 delta E1 plus 1 over T2 delta E2. Okay? And the next step is to say, well, but we kept the total energy constant. So if the total energy constant, delta E1 equals minus delta E2. You can modify the energy of this system a little bit. Okay, you can lower it, and then the energy of this system will go up, or you can lower the energy of the right-hand side, and then the energy on the left-hand side have to go up. But the total energy was kept constant. Okay. So what happens is 1 over T1 delta E1 plus 1 over T2 minus delta E1. So I obtain the following equation. 1 over T1 minus 1 over T2 delta E1. Now, remember this constraint? That whatever I have calculated, this delta S, it has to be smaller or equal to 0. You introduce some perturbation, guys, something happens to the system, and you know that the effect of this perturbation is either 0, basically almost haven't done anything, or it's smaller than 0. But delta E1 was completely arbitrary. Okay? So it holds for any delta E1. When this equation can hold no matter what delta E1 is positive, delta E1 is negative, it's large, it's small, it will always hold, and it will always hold only for one specific condition, when 1 over T1 equals to 1 over T2, namely T1 equals to T2. That's the result. The result of the maximal principle for entropy means that when you have two systems in a contact and those two systems are in equilibrium, the temperature of one part of the system equals exactly to the temperature of the other part of the system. Okay. This sometimes called a zero law. So if you take two bodies, you contact them, you wait a while, and the temperatures, this is the equilibration, the temperatures will be equal to each other. We haven't started with this assumption. Instead, we started with assumptions about entropy, okay? And then we obtain this law over here. Yes?
I wanted to ask, when you calculated the variation in the entropy...
There is no information. We haven't talked about...
Variation,
okay.
Don't you need to add a term for the partial derivative of S by T?
No, because T are not the variables of the system.
But
T are not variables of the system. Okay.
But
I will describe it in a little bit. T is not a variable. T is not a variable. Remember the equation? So this is important, people. D equals to TdS minus PdV. What are the variables? The variables are only those things that stands as a differentials on the right hand side. So S is a variable, V is a variable, P is not a variable, T is not a variable. Okay?
So don't we need to add another
No.
derivative for V?
No. If I kept it constant, I don't. But well, it depends if I modified V or not. I haven't modified V. Any other questions? Okay, so this example, yes?
When you write a delta like this, when you wrote on
It's not a differential, it's a small change. It's a variation.
But
Okay?
I thought energy is independent of the part.
Well, I haven't told you what exactly have I done. I just said I've done a perturbation to the system such that there was a modification of the energy of the left-hand side and the modification of the energy to the right-hand side. Mathematically speaking, I've performed a variation of energy somehow. Okay? Great. So this example, we started at equilibrium. What will happen if we will start out of equilibrium? Okay. If we start out of equilibrium. Okay. So I had two systems. One had E1, T1, S1. The other one had E2, T2, S2. I connect them, okay, and I look what happens. Okay. So first of all, now the system, so I take my adiabatic boundary conditions. I put the adiabatic boundary conditions on top of those two systems. Adiabatic boundary conditions. Okay. And I let the system go. So what will happen? Due to this adiabatic boundary conditions, what do I know? What happens when the system evolves on its own and everything is adiabatic? The entropy has to grow. Right? This is the assumption. If I'm starting from state A and I'm reaching state B adiabatically, the entropy grows. Second law of thermodynamics for us. Okay. So what we know that delta S is greater than 0. What is delta S? Is delta S1 plus delta S2 is greater or equals to 0. Again, the same trick as I did before. What is delta S? Is delta S1 to dE1, D1, or delta 1, plus ds2 de2 delta e2, okay? And I know, so this is delta S, and I know that it has to be greater than 0 this time. Again, the energy, the total energy, there is no escape of the energy to the outside. I assume that the energy is extensive, so the total energy E equals to E1 plus E2 and constant. This means that delta E1 plus delta E2 equals to 0 and delta E1 equals to minus delta E2. The same tricks applies. This is 1 over temperature. This is 1 over temperature. See, the only thing that I've done, I've played with is entropy larger than 0 or smaller than 0. So what we obtain over here is that 1 over T1 delta E1 plus 1 over T2 minus delta E2 minus delta E1. This is greater than 0. So I obtain this 1 over T1 minus 1 over T2 multiplied by delta E1 greater than 0. Okay. Now, so out of this, it starts to be a little bit more interesting than the previous example. So what will happen if delta E1 is greater than 0? What I mean is that I made a contact and a heat has flown from the system on the right hand side to the system on the left hand side. Okay. So if delta E1 is greater than 0, then this guy is also greater than 0, right? So if this guy is greater than 0, T2 is larger than T1.
No, the opposite. What?
Why?
No, no.
Yes. Yes or no? This is greater than 0. This has to be greater than 0.
Yes, no, that's right.
It's okay? So what it means, again, I started with two systems. The systems somehow equilibrated. They equilibrated by doing what? That some portion of the energy have flown in terms of heat from the right hand side to the left hand side. It means that the temperature on the right hand side was higher than the temperature on the left hand side. Right? A trivial fact. But since we don't really know what temperature, it's some derivatives, etc., okay, it's reasonable for us, but we got it. Okay, so heat flows from hot systems to a cool system, from systems with higher temperatures to the systems with lower temperatures. I do the same thing if delta E is smaller than 0, right? I will obtain that T1 is larger than T2. The same idea. If heat has flown from this part, from the left-hand side to the right-hand side, it means that the temperature of the left-hand side was higher than the temperature on the right-hand side. Right, trivial, we understand it from daily life, right? So if I somehow can connect two systems, one is hot, one is cool, eventually the hot system will get cooler, the cool system will get hotter, and it means that heat had flown from one system to another. Where it always flows? Flows from the system with higher temperature to the system with a lower temperature. That's it. Okay. And it all related to simple principles of what is entropy and how it depends on energy. That's the only thing that you have to assume. Yes? Questions? No questions. Yes?
The first one, we were in equilibrium and now we're not.
Yes.
Okay.
Two different examples. Okay, great. What else I want to tell you about those variational principles? And it's actually related to the question that was raised beforehand. Why I'm taking derivative with respect to S and I'm not taking derivative with respect to T, and what are exactly the variables of the system? Okay. Question is, what are the variables of the system? And the answer is, because it's like a mathematical theory, you have to look on the function you are interested in. And the only function that we have so far is the function for the energy, right? So for the energy, we developed the following function from the first law of thermodynamics, that dE is T ds minus P dV. And if we have some sort of a tension inside the system, so as plus tau dl, for example. Okay? And we know that those are generalized coordinates, variables, and those are generalized forces. Okay? So variables, forces. Okay? So from a mathematical perspective, when I write a differential of any function and I get a bunch of different differentials multiplied by something, it means the following. So for this case, I know that E is a function of S, V, and L. Okay? Whatever stands in the differentials are the variables of my system. Okay? This is how I recognize them. Whatever stands in front of the differentials, those generalized forces, is the derivatives. So T, it is dE to ds. And minus P is dE to dV. And tau is dE to dL. Now here I have to get everything else constant. So here it's V and L is constant. Here S and L is constant. And here S and V is constant. So the answer with respect to what to take a derivative and with respect to what not to take a derivative, the energy depends on whatever stands in the differentials. So it is S dL. Any other my generalized forces are how the energy of the system is modified when I modify one of the generalized coordinates of the system. That's it. Okay? So force is always how the energy, it's always, for example, you remember this from mechanics, right? So F is minus du dx. Right? So if I have a potential energy and I take the derivative of this potential energy with respect to a coordinate x, I have a minus over here, I get a force. The same thing happens over here. The moment I have written my differential for the energy in this way, this is those prefactors. This is why I call them generalized forces. The same idea comes from mechanics, is how your energy is modified with respect to modification of one of the coordinates. Great. Now, are those the only generalized coordinates that we will treat in this class? The answer is no. There are many coordinates, generalized coordinates that you can use. Mainly we will use entropy, volume, length. We'll later use magnetization, but for now on, we can also use the number of different species or different kinds of particles that we have inside of our system. So let's assume that I have N1 is the number of black particles, and N2 is the number of red particles, and N3 the number of purple particles inside the system. So in general, when I'm writing my energy, I have to assume that it depends on the entropy. It always has to depend on entropy. Volume, okay? Let's assume that I have a length of my system, but it doesn't really matter. And it can also depend, for example, on the different kinds of particles that I have inside the system. So it can depend on N1 and on, let's be consistent, and N2 and N3. Okay. The presence of different particles, different molecules, okay, affects the energy. Now, so they have to be present somehow. This means that dE, it is what? So we know it is dds, we know it's minus p dv, we know it's tau dl, okay? And since those are generalized coordinates, the energy depends on n1, n2, n3. So we'll have here dn1, we have here dn2, and we have here dn3.
Each one has its own constant?
Sure. So I will call this guy mu1 plus mu2 plus mu3. And this is chemical potential. Chemical potential.
Are you including the interaction between the molecules?
So, in some sense, yes. So it depends on how many molecules of this guy, etc. Now, the answer to your question is, what exactly are mu1 and mu2 and mu3? Okay? And that's important. So, in general, mu1 can depend on n2 and n3, okay? And then the interactions are included. So, you can say, well, Stas is just a definition, but if I'm including additional particles inside the system, the energy of the system can go up or it can go down. Therefore, it has to depend on those constitutional numbers. Okay? And the chemical potential is simply as over here, the derivative of the energy with respect to the associated coordinate. So we have over here that mu1 is dE to dN1, and mu2 is dE to dN2, and mu3 is dE to dN3. Now, if you think about another generalized coordinate, okay, it's important that this generalized coordinate has to be extensive. Okay, I will define a generalized force, which is going to be simply the derivative of the energy with respect to your new generalized coordinate. Now, since E is extensive, S extensive, B extensive, F extensive, N1 also extensive, N2 extensive, and N3 also extensive, what is T? It's intensive quantity. And P is intensive quantity, and tau is intensive quantity, and mu1 and mu2 and mu3, they're all intensive quantities. They are independent of the size of the system. Okay. Great. So we have 20 minutes left, and the thing that we will do next, after we have those generalized energies and entropies and variational principles, is to ask the following question. Well, I'm a theorist, so I don't really care how things are measured inside the lab. But let's assume that I want to cooperate with experimentalists. Okay. So you pick up your favorite experimentalist in on our department. For example, I will pick up Eli Slutskin, and I will come to Eli Slutskin lab, and I say, Eli, I want you to perform this experiment, and I want you to make the entropy to be 10 something. I said, what? Yeah, the entropy for this experiment should be 10. He will kick me out of the lab, or he will, because Eli is nice, so he won't kick me out. He will say, well, Stas, I don't know how to make entropy 10. Or he starts to argue with me, maybe we'll make a heat, or we want heat, or we will head the system. The entropy, and this is related to your question, it's a very, I won't say mysterious, but not really properly defined quantity so far. So when I'm talking about energy and that it depends on the entropy, it makes the life for all the experimentalists and sometimes also the theorists really hard, right? Because it's not a very natural quantity to operate with, right? So how can we make our life simpler or more natural and look on everything, including our variational principles, without looking on the entropy? Okay. So basically what I want to say is I want to perform or to display everything in terms of variables that do not depend on the entropy at all. Okay. What I mean is as follows. I know that S is somehow depends on E. There is some sort of a dependence, or let's make it the other way around. E somehow depends on S. Okay? And it grows somehow. Okay? And I know that E is a function of S. Now I want to perform some sort of a change of variables such that I will encapsulate the physics of the problem, but I will get rid of this variable S. Okay? I don't want it over there. I'm trying to make a change of variables such that I would obtain a function that is independent of S. Okay? So what will I do in order to get this function? So we look on this specific point over here. And at this specific point, it's, we can say, well, this is S1, and this is E1. Okay? Now, I would like to make the following construction and define the hobby, but then the behavior of the system is encapsulated of how exactly A is growing as a function of S1. Now I want to describe the similar curve, but I don't want S's and E's inside. Okay, so what do I do? So first of all, I want to describe the curve not just by taking the position along the x-axis and the position along the y-axis. I would take the derivative or the slope of this curve at this point, E1, S1. Okay? But it's not enough, right? Because in order to describe this curve, I need a bunch of two coordinates. I need S1s and E1s. Okay, so what do? So I take the slope, or this tangential line, to this point, and I will continue till it crosses the y-axis. Okay? And over here, I will describe this point as F1. Right. Now, what do I have? I have the slope, okay, or of this tangential line, and I have another point that crosses the y-axis over here. And what I'm claiming, that I can describe this whole curve instead of looking on the x coordinates and the y coordinates. I can describe this whole curve by looking on the tangents at each point and the crossing points of the y-axis. Okay? Why should I do it? Why should I do it? So I can do the following thing. So what is dE to ds at this specific point? How I obtain this slope? I can do the following thing. I can say, well, it's actually E1 minus F1 divided by S1 minus 0 equals to dE to ds. Do you agree with me? At this specific point, the tangents to this line, or the slope of this line, is just the delta y divided by delta x. Delta y divided by delta x is the slope, and the slope, or the tangents of the slope, is exactly this derivative over here. Okay? But this guy, dE to ds, it is t. Right? The derivative of the energy with respect to the entropy is the temperature. So I obtained the following transformation. Instead of saying along the curve, this curve encapsulates what the physics is inside the system. So instead of saying what is the x-axis and what the y-axis, I would say what is f and what is dE to ds. Okay. So from here on, I obtain E1 minus F1 equals to S1 multiplied by t. Okay. Or F1 equals to E1 minus S1t.
It's like Helmholtz.
Legendre transformation. Now, I don't care about if I do it for specific E1 as S1. I do it for any E and S. And then I obtain the representation of this curve, okay, in terms of F equals to E minus ST. You can say, well, Stas, this is great, but it's not clear why it's helpful at all. Why to do this? Okay, so you can maybe can invent some other function, okay, that is going to describe this curve. Why to do explicitly this Legendre transformation? So the Legendre transformation has another interesting property. Okay, so this is just a transformation. In order to understand what are the functions or what are the variables that f depends on, I have to describe what is d of f. So d of f is d of E minus st. It is the differential of E minus the differential of s of t. It equals to d of E, we know what it is TdS minus PV, okay, minus PdV. And here I have minus S dt minus T ds. Okay. So this guy goes into this formation. Specifically, TdS cancels out, and we obtain that df equals to minus S dt minus P dv.
Plus the
Plus what?
d.
No? Where's d? d disappeared.
Oh.
Instead of d, we have written TdS minus PdV. Okay. So what we obtained that f is a function of what? Temperature and volume. Okay. So this is the point of why I have to perform this Legendre transform. Legendre transform. Okay. Legendre transform is specifically designed to make a change of variables such that if you have a function, and I remind you, dE equals to TdS minus PdV. And if what you want to do is to describe a new function such that instead of using S, you would like to use as a coordinate whatever stands in front of the differential of S, you perform this Legendre transform. F equals to E minus ts. Okay. If for example, I would like to make a different kind of transformation. I could say to you, look, I'm fine with entropy, but I absolutely don't like volume. I don't like volume. I want a function that is a function of S and a function of P. Okay? And a function of P. So what should I do? I would again describe to you A as a function of something. I would perform a Legendre transform, and this Legendre transform would look like H will be as E minus P V. Okay? So whatever the coordinate that you want to get rid of, okay, you take the original function, you take minus the generalized forces multiplied by the coordinate that you want it to disappear. Okay. Let's see what happens. So dH equals to dE E plus PV. It equals to dE plus dPV TdS minus PdV plus PdV plus VdP. You obtain that dH equals to TdS plus VdP. So H is a function of S and a function of P. By using those Legendre transformations, you can transform from one coordinate to another coordinate. Those coordinates, it's not just you can go from S to V. This is not allowed. The only thing that you can perform is to go from a coordinate to whatever is called a conjugated coordinates. Okay. So if we write our energy, once again, dE equals to TdS minus PdV, let's assume plus mu dN. Okay. So S and T, you can go and describe a function in terms of either S or in terms of T. You can go from P and describe it either in terms of V or in terms of V. So let's do it V, P over here. You can go from N, the number of particles that you have inside your system, or mu. Those are called conjugated variables. And you can pick up whatever variable that you prefer. You can pick up either S or T, either V or P, either N or mu. Why? Well, it depends on the problem at hand. It depends exactly what you want to describe and what you want to solve, etc., etc. The thing is that any transformation is modifying your energy. So energy is a thermodynamical potential. Now, when you modify the variables of your thermodynamical potential, you still have some kind of energy, right? You started with the energy, you modified the coordinates, but it's still an energy. So all the other quantities, and G, it is E minus TS minus P V. It is Gibbs free energy. F, which is E minus TS, it is Helmholtz free energy. What other stuff that we have? H, E minus P minus B, it is enthalpy. And psi, which is E minus TS minus mu n, it is grand canonical potential. All of them, absolutely all of them, are energies. All of them thermodynamical potentials. It's just the different coordinates that we use in order to describe them are not S, V, mu, L. It's something else. Okay? So for F is D, V, and N. And for G is a function of T, P, and N. And for H, it's a function of S, P, and N. And for psi, it's a function of T, P, and mu. You want to use a different coordinates? Do as you like, as long as those new coordinates are conjugated to the old coordinates. This is great. And also, something else, which I won't prove to you, but the proof goes exactly as it was done for the energy. At equilibrium, all the thermodynamical potentials are at minimum. So there is a general variational principle that is applied to any thermodynamical potential that you like. You want to look on the Helmholtz free energy, at equilibrium it's going to be minimal. You prefer to use chemical potential, okay, and temperature, so look on the on the grand canonical potential, it's going to be at a minimum state value. Why to use this or that depends on the problem. We'll see that the most important for in this class is going to be Helmholtz free energy and the grand canonical potential. But in chemistry and chemical physics, they use all kind of different functions. It will depend on what are your variables that you prefer to use and what is the problem at hand. So we'll stop here and we'll continue to stability because it's just saying something about the minimal. What we haven't told you, I haven't told you, is this minimal stable, non-stable, and how it affects the different parts of the system. Thank you very much. סאי? למה בי?
לא פיצלת אותו.
צודק. אתה צודק לגמרי. תודה.
אני גם עשיתי, אבל יש מספר אליי. אני גם עשיתי
לא, זה תמיד לא. אני בוחר באיזה פוטנציאל להשתמש ואני משתמש